Okay, guys. So we finished example 9.3. So now we are in quick check 9.6. This is saying which force below does the most work. So if you take, let's just say this one first off, okay? And we do 6 newtons, and let's just plug in the R as 1. Or actually this says, let's just say the R is 1. So 6 newtons times 1 meter, and let's just say cosine, I meant to put a 0 in right there. Okay, so if you do 6 times 1 times the cosine of 0, then you should get just 6. Okay, so you end up with 6 joules, right? Now let's say that R is still 1 for this one. So now we've got 8 newtons times 1 meter times cosine 60 degrees. So now if you do that, 8 times 1 times cosine 60 degrees, you should get 4. And then, of course, this right here is 90 degrees. So do 10 newtons times 1 meter cosine 90. And you should get 0. So that's what I was saying earlier when I said it wrong on the last video, I think. When I said that cosine 90 was 1, and then I said, oh wait, no, never mind, that's 0. So if you have a force that's going like perpendicular or at a 90 degree angle from the direction, then that is considered to have no work done. Okay? But if there is any kind of angle to where it's not parallel is going to have the most work. Okay, so in this case, then the answer is C. Yeah. But if there is any kind of force / displacement that has some degree of being parallel, so besides 90, 90 is 0. But anything around that either has some positive work, like in this particular case, the displacement is somewhat in the same direction as the force. So that would be considered to have positive force. Now, if it starts to go the other direction, like this way, that's when we start getting into those negative work situations. Come on. I don't know why my slide's not going. Okay. So, let's see. I think here we are. Maybe. Yep. Okay. So, now we've got, let's see, example 9.7. So this is saying that you've got a light plastic cart and a heavy steel cart are both pushed with the same force for a distance of 1 meter. Starting from rest, after the force is removed, so now there's no force that's being, it's been removed, okay? The kinetic energy of the light plastic cart is blank that of the heavy plastic cart. So after it's been removed, and it did say though too that it had the same force and they both went a distance of 1 meter. So the kinetic energy or the work, remember those things are interchangeable. So if they have the same force, let's just say 1 newton times 1 meter, it doesn't matter if one's a light plastic cart or a heavy steel cart. Either way, they had the same amount of force, the same amount of distance, so they were equal to, okay? All right, dot product. So you'll get more into this, I believe, in Calc 2 and definitely in statics next fall. I think it might be next fall. I don't know. They're still back and forth on it. And so we do a little bit of it in here. It's not a lot. And you'll end up I think you'll end up liking it whenever you get into statics because it it makes it's more applicable. But you do see some examples here where it kind of comes into play, just to give you kind of like a broad, overview. The dot product is a scalar product, which just means that it's a number. It's not telling you any kind of direction. It's just telling you magnitude of the forces here. So in this case, you've got vector A and vector B and some sort of angle in between them. So in order to do the dot product, you literally just take the two vectors, cosine the alpha, or that angle. So what this is trying to get you to see is what I just sort of said before. If you are parallel and you're going in, the same direction, then that's going to give you your maximum amount of work there. Okay, so just A times B is equal to AB. That's the vector. There's absolutely no angle there. If you are going at this angle, which is what we were doing in that last quick check, that dot product then is greater than 0. So that's positive. Okay? If you have a perpendicular or 90-degree angle, then that's like what we said earlier, it's 0. If you start going the opposite direction, then you're going to end up with a dot product, but it's going to be a negative. It's going to be less than 0. And then if you are completely 180 degrees, then it's, still equal to A times B. It's just negative. So it's just basically the exact opposite of that one, right? Just negative work, like what we had done a couple of slides before. Okay, this one, I don't know what I just did there. Okay, apparently I didn't give you the example, like the typed out, because what I think happened is it had all of the answer on it, so I wanted us to actually work it out. If you look in the text, you would see that there is an image that kind of looks like this. How I am at drawing. It's really kind of sad. I used to think of myself as a pretty good drawer, and now I think I'm just really getting terrible. Vector A is 3, and vector B has a value of 4. And in between here, we've got 30 degrees. So literally all you do for this dot product situation is it's just, I'll go ahead and write the equation as it was on the other slide. You just do your A, B, cosine, whatever that alpha or degree between them is. So it's just 3 times 4 cosine 30 degrees, which should give you 10.4. And there's no unit or anything on this particular vector. This is just kind of showing you what you have to do whenever you're doing dot products. And okay, so on this one, this is going to get you into some of those Cartesian vectors, which you have to use a lot, again, whenever you're in calculus, like the higher levels, and statics. All those tell you is which direction you're in. So, I for your x, j for your y, and whenever you start using z, that'll be your k. So, whenever you start getting into 3 dimensions, you have to throw in a k. But for now, you should be somewhat familiar with I and j because we had to do that whenever we did vector addition. Okay, so whenever you're doing the dot product, basically you have to just figure out the x components and then you'll multiply those. So whatever the x component of vector A is times whatever the x component of vector B is. And then you literally just add them. You add them to the y components of vector A times vector B. Okay? So let's see. I think there's another example. And I didn't put this on here because it did the same thing as the last one. So let's see. You guys will just have to draw this on your own. Okay, so we've got 0 and then 1, 2, 3, 4, and then -1. I think that's all I have to go to. And then I got to go like this. So -1, something like that. All right, so this first vector A is just like 3, 3. Okay, and then vector B is 4, -1. This. Okay, so let's check out vector A. Vector A's, how you would write it as far as Cartesian, you would do 3i, and you could say plus 3j. Okay, so they're both positive, right? Vector B, you've got 4i, but you are in the -j. Okay, so 4i minus 1j. Now, as far as the dot product's concerned, you have to separate them into their x and y components. So 3 times 4 plus 3 times -1. Okay, so you end up getting 12 minus 3, so 9. That's your answer as far as dot product is concerned. Hopefully that's not too bad. You know, if you have a question or something, let me know. You know, sometimes the homework is a little different. I understand. All right, so work done by a constant force. So as the force acts with a constant strength, so the same force, okay, constant, in a constant direction, the particle moves along a straight line, and through a displacement of a change, you know, we went from an initial position to a final position, so we get this equation, which I swear we had a long time ago. So now we've got another example that I think I have to write again. Okay, so this one, I'm going to actually write some words that you might want to copy down. So this says that a 70 kilogram skier is gliding at 2 meters per second when he starts down a 50-meter long slope, and it does say that it's very slippery, of 10 degrees. What is his speed as he reaches the bottom? Okay, so let's kind of draw this out, free body diagram, for a minute. So they kind of start, you know, up here, and they go down this slope, and this is a 10 degree, right, slope right here. So if we were looking at all of our forces that were involved, now this right here we need to say is 50 meters. But just remember, we have normal force, which is perpendicular, and then we have this this gravitational force right here. Okay, so this one right here, if we were doing the dot product of that 90 degrees right there just sort of wipes it out. But this, there's an angle right there, right? So what is it? Well, this right here is actually going to be 80 degrees. Because this angle right here would be 10 degrees. Okay, so anyway, this is ultimately wanting you to find the speed at the bottom. So let's write some stuff down, okay? we've got that their initial position is, we'll just say that's 0. And we know that the final position is 50 meters. The initial velocity is 2 meters per second. So there is an initial velocity, which is important. And we're wanting to find the final. And it does give us the mass of the skier, which is 70 kilograms. Okay, so now we need to figure out, I just said earlier, this normal force here, since it's at a 90 degrees, that's just going to sort of wipe that out, right? But this force of gravity, you know, if you do that times distance times that cosine theta, or in this case it would be, you know, this alpha that you've got here, okay, then you can end up figuring the dot product of it. So you've got 70 kilograms times 9.8 meters per second times this distance of 50 meters times this cosine of 80 degrees, and you end up getting 5,960 joules. Okay, but that's not what it wants. It wants us to find the speed. So if you remember from a few slides ago, it says the change of kinetic energy is equal to the work. Well, we just found the work. So the change of kinetic energy means final kinetic energy minus initial. Oh no, I think my pen is going out on me. Hold on, let me see if I can plug it in for just a second. I don't know, I might not be able to. If I can't, then I'm gonna have to stop the video and start a new one. Right in the middle of an example. Ugh. Okay, let's see. Yep, nope. I'm gonna have to stop it. Sorry, guys. If I can stop it. Oh no. Okay.